Yeah, fine. So we'll review what we had discussed in the previous sessions. So essentially, we are attempting to solve a bar extension problem, which is this here. In the, so, and it's a bar with the left hand fixed and a terminal load applied on the right hand side as well as the distributed load here. And E is the Young's modulus, A is the area of cross section, and the E governing equation is d by dx of E of x, A of x, d by dx by dx plus f of x. The one thing with, say, with Phoenix, right, is we won't have to, when we write our own code for a general, right, then it becomes a complex process. It's no longer just assembling. We actually have to compute properties and then construct the matrices. So this is the governing equation, and then our boundary conditions are fixed on left-hand side and then free on the right-hand side with a terminal load, actually. So it's like concentrated terminal load on the right-hand side. And the usual process of FEM, we have the strong form, multiply with the, so multiply with the weighting function here, and then up to integrate by parts, and then we are able to have, so this is the weak form. Yeah, this is the weak form, yeah. And so this is an effective weak form. And then we went on to describing about the discretization of domain, defining basis functions, and then approximating both the geometry and the solution functions using those basis functions. Then we had this Galerkin weak form. And then, yeah, we defined the new subspace, solution subspace. And then we defined this isoparametric element, and then define also the Jacobians for change of variables. And then we would wanted to create a template to do all these integrations. Since there are lot many integrals here, so we wanted to form a template for. And so we were able to create a template. Say any what you call element of the physical domain, we were able to express in terms of the bi-unit domain, which is -1 to 1, and that we were able to do it here. And then so now our say so far it was all based on what, when E, F, and A are all functions of X. How do we do all that? But the thing is, for that we have to, all that we need to do is do proper bookkeeping. However, if E and F are constants, then it becomes a completely uniform beam. So then just having one isoparametric element, defining it integral over a domain, and then assembling it. So that is the only job we have to do. So it becomes, the job is much more simplified. But so what we are doing here is we just consider uniform bar and then defined all these. We're able to make all these integrations and pose it in terms of a matrix vector product. Essentially, vector matrix vector, so it becomes a scalar. And likewise for the forcing function. And now we are able to assemble everything into one place, and then even assembling the forcing functions. Force comes on the right hand side, and then we try to eliminate these arbitrary constants on the left hand side, which are nothing but the arbitrary constants of the weighting function. So and then eventually we were able to even add the boundary conditions, and this is our final matrix system of equations that we are going to solve. Yeah, so what we had said that, okay, we'll be solving it and solving this matrix system and comparing with the analytical solution in Python or MATLAB. But yeah, we solved it using Phoenix and compared the results. And then we would also be generalizing approach for arbitrary E and F. The thing with this is, if we write our own code, then it's just about proper bookkeeping. There is no such additional complexity. So with this, I will just switch to I'll just switch to the code here that I have. So yeah, this is essentially our code using Phoenix package. So what we are doing here is
sharing it. It's not being shared yet. Yeah, now it is coming up. Yep.
Okay. Maybe I also just switch off the camera to preserve the bandwidth and all. Okay, so these are schematic of the axial deformation of bar. So this will bar equilibrium position and then deformed configuration. So any segment located at X will undergo a displacement of U. So that is essentially what we are solving here. So we'll go through the Phoenix. So we'll be using Phoenix package. I think it's well known to all of us. It's a package. It's a header. Sorry, it's a library for FEM, which is whose wrapper is in Python, but the backend is in C++. So Phoenix, I'll just to review because I think this happens to be a very important concept. So Phoenix is composed of three different things. It's composed of fundamentally it's composed of uh, Dolphin, UFL, and there is something known as basics as well. I think it will be just basics. I think just this. I forgot the actual spell. Yeah. So Dolphin is what we call as the FEM engine for Phoenix library. So it does everything, all the FEM, what we call uh, handle or what we call all those helper functions. That is actually contained in the Dolphin package. And UFL, its aim is to provide some unified form language for mathematical expressions, such that if you write a grad, so that is equivalent to grad is equivalent to what we do, what we'll ideally just apply nabla operator. So if you are using divergence, that is equivalent to doing some divergence, finding the divergence. So that is what it does. And if we say write inner, then what it does is we have to give it two arguments, and it will find the inner product between two different functions or two different elements of the vector space. So that is what it does. So essentially, it's all symbolic in nature. And NumPy is, as we know, it's the most powerful library in Python because it has all the functions, methods which are essentially required to perform any numerical task in Python language. And matplotlib is the plotting library, and it has syntax. Syntax is very similar to MATLAB. So that is why it's essentially called matplot library. Yeah. The developer who actually developed this matplotlib, he passed away around 2 years back. Yeah, just
2 years,
so
or has it been so many years?
no, just 2 to 3 years back. I recall. He just
I think even he left as well. I think for cancer. I think, yeah.
yeah, something like that. Yeah,
It's
he
true.
created the most powerful alternative to MATLAB plotting system.
Yeah.
And then we also use MPI. So MPI is, even if we don't use MPI, we still have to define a network when we are dealing with when we are using this Phoenix packages. And then there is something known as PETC. So PETC is very much like a linear algebra library, and it's fully parallelized. So that is the advantage of using PETC. So once we have, so these are the most important. This one is just for when we require it anytime. Import sys, but right now we are not using it. We'll use it gradually. We'll come to know where to use system, where to use time, and how can we use OS and all. So for now, I'll just comment it. So, okay, we start with our parameters. So the fundamental parameters are length. We have taken it to be 1 meter, and Young's modulus to be 10 power 9. And A is equal to 0.01 in meters squared. And the number of elements we are taking is 99. Now what we do is the next step will be discretized. So we create a 1D line mesh with 19 elements or 100 nodes. And we have to, and the endpoints are 0, comma length. Now we construct the domain, or we can also call it mesh. So this is, for that we have to use So since domain discretization is a part of FEM, right? So that's the reason we use Dolphin package.
Mm.
So dolphin dot mesh dot create interval. So we prescribe the interval and then define a communication network, which is mpr.com. Well, this we just have to do because yeah, that's how the newer Phoenix has been designed. And then we specify the number of elements that we would like and also the endpoints. So which means this function takes three arguments: the communication network, the number of elements, as well as the number of or the specify the endpoints. And then I'm just printing as to how many cells it has. This is not required, but yeah, just for to say, I mean, to check whether it really discretizes 19 elements or not.
Uh,
Now we, uh-huh,
yes, yes, yes.
yeah.
That's
So
fine.
now we come to, yeah. So now we come to the fundamental thing here. Uh, from the math, I mean, approaching it from a mathematical perspective. So in FEM, we first define what is the function space.
Mm.
So, and then in Phoenix, the way it's designed is we first have to define function space over the entire domain, which means that we are already specifying, uh, we are already working in Galerkin weak form. So we are already in Galerkin weak form. Since the thing is, what in finite element literature we call as V underscore H. So we are actually defining that only. So we are defining this function space over the discretized domain using Lagrange polynomials of order one, which means that we are using linear polynomials or piecewise linear polynomials. Now, so
Mhm.
once we have defined the function space or the vector space, now we just define the test function and the trial function. So U is our trial function. So the way we define, so since we are using a mathematical language, I mean, to denote some mathematical quantity using some language, right? So for that we use this UFL package. So what it does is, as we recall here, that it just translates mathematical statement, I mean mathematical terminology into programming framework. So that's what it is here. So U is equal to U of UFL dot trial function, and likewise V is equal to UFL dot test function. So which means we have defined both trial and test functions. And at even just what we'll do is we'll even define the solution function as well, even if it's unknown right now. So that our solution will be actually stored in underscore sol variable. So
So when you say U solution,
uh,
and you're giving the same function space, no? So is
yeah,
this like we will interpolate and save in this U solution at the end after getting the values at discrete points?
yeah, actually, so what we'll do is it will be stored in usesol directly. So, and the
Okay.
thing is, it will be fully defined over the domain, fully defined. So it means it
Yeah, I mean,
inherits
yeah,
all the
exactly.
all the
Either,
properties of, yeah, yes. So it
yeah.
inherits all the property from the from the function space V, and that is what we require essentially.
What does this one mean here, Krishna? Lagrange comma one मतलब क्या है?
One means linear,
Yeah. So
and
I
two,
think U solution is something. So you compute the values at discrete points wherever you discrete like nodes. I don't know what you
uh-huh,
call them here. Then
uh-huh.
U solution will, so it is taking the function space because function space it knows that I have to interpolate using these linear functions and it will give you a solution at whatever point we want. That's what I think it does.
Uh, Another thing is even you will score only the discrete points.
Okay.
It's just that it will be an object, right? So it will have many things defined over it, which means that if you say u sol dot norm, it can give us the norm of that entire solution. So it's just
Okay.
like we want it to inherit all the properties, so that you know that we will have so many attributes associated with it, so many
Yes.
attributes,
Yeah.
like attributes like size, the length, and the shape, the norm, and all. Those all what you call operations can be performed on you directly just by calling it say v dot norm and something like, I mean, all those things. Maybe I should also give a short review course on Python, but yeah, but later, yes. So we have defined useSol and also assigned the name displacement. So it means this useSol we will call as displacement when we are saving our solution file. Now, once we have that, now we would like to define the source term, or what we call as the forcing term. In that, what we do is we first say if our forcing function happens to be a function of the space, then we would also like to have the location or the Cartesian coordinates of every nodes. So when we call UFL dot spatial coordinate and giving the argument as the domain, then
Can't hear you. Oh,
Yeah, Krishna.
I think he's
how
gone.
about now?
Yeah,
No,
now
but
I
I
can
can
hear.
now-
Okay, so I'll just repeat. So X is like it stores, it gives us the spatial coordinates of the nodes in the domain. And then say if we want to define some variable forcing function, right, which is a point dependent, then we again have to use the same thing, which is dolph. We again have to define it as a function over the domain. So it's like f varying. We need to first define dolphin.fem.function that, okay, let's define the function first, and then we can interpolate using, say here, what I'm trying to do is I'm trying to have forcing function as 10 into sine 2 pi of x. So this is what I'm
Yeah.
giving as the forcing function. So you see how
Value.
beautiful it can be. Yeah.
So f varies with like pi jaise, but just handle it with 10, no?
Yeah. Yeah. So it's like, yeah. So it's like now you can see that like this has different values at different x. So we are very easily able to do that by
So last time you
interpolating the
didn't do
function.
this. So this week you are
No,
adding
no.
this new term, no?
Yeah,
Yeah.
yes. So I was just trying to learn that how can we have varying functions.
Amazing.
Yeah, so it's like we are able to clearly define this f dot varying dot interpolate, and then now we have this I mean the forcing function in discrete form,
So,
and then at the
so
same time
just
also defining a constant forcing term. Sure. Yeah.
interruption. Sorry,
Ah,
interruption. So I think if
sure.
say we are dealing with non-linear structures like shell or anything, I think everything stays same. Just that the way you define the domain changes and the way you describe the domain changes, right?
Yes, that's true. That's true. This
Right.
interpolate happens to be a very powerful function. It can be used everywhere. Since the thing is FEM, I mean, Phoenix considers every domain as 3D, right? So inherently FEM, I mean, Phoenix is what you call is a 3D finite element software. So you will notice one thing, that when I'm defining this, so this this is known as the anonymous function in Python.
Okay.
Yeah. So anonymous function is function for whom we do not provide any name. It will be only visible right at this point, and at
That's
any
lambda.
place we want to. Yes. Yeah. So this is
That's
like
lambda. No?
also called as lambda function. Yeah. So you clearly see that 10 into np dot sine 2 pi into x naught. So x0 is the first element in the x coordinate here. So first element will be, so I'll just say that. So x0 is equal to x, and x of 1 is equal to y, and x of 2 is equal to z in 3D space. So that's why you see that, so everything is in 3D. So once we have defined the forcing function, now we can also have the constant forcing function. So this was the variable forcing function. Now we'll also define constant forcing function. In this case, we have dolphin.fem. Till now it's the same because we are still working in FEM framework. and then defining constant here. And then we'll say that on which domain we need to we want to define this constant, and what should be the data type. So there is in Dolphin, there is Dolphin.default scalar type. So it's just a way of, even if we don't write this, right, we can directly write 6. That is also value. I mean, this is also valid. So which means, yeah, this is also valid, which means that we are defining a constant forcing function of value 6. However, this is like, I mean, I have seen people just defining it like this. So yeah.
No, I think due to maybe, I mean, it's a bit deeper, but I don't know how much relevant. What I'm saying is relevant to the current discussion. I mean, scalar ka matlab. So even PETES, sometimes you solve for F32. Okay, sometimes
yes,
double. Okay,
yeah,
and if you just
yeah.
write 6, it's a scalar type. So 6 is int, ki double hai, ki float hai. So when you're solving,
yeah,
no, you in the background, because this Fortran and all this stuff, they need what exact type it is. So in a way, you say default type ye hai, then automatically Dolphin last mein it will set everything up and say, okay, 6 boss, set it to some double or long double. We don't know. So that's why you mention it as default scalar, whatever type. No, the background is the जो manager है वो, इसलिए you give just 6 scalar है boss. If you say vector, no, vector also automatically taken care, like, okay, because it may inside it may make it into like 6, like even though you give three-dimensional vector, so the software might be written such that it is for 4-dimensional, right? So it will only set those 3 dimensions, and 4th dimension it will leave it, and that's why you give it like this.
Right. So one way is this, and the other way is we can also define as something called as say, I'll just copy this statement. So we can also define in terms of using PETC data structure. So in that case, we'll call it PETSC dot scalar type. So I have used somewhere else, so that which means that we can have both. So I just, that is what we have done here.
I think ultimately you're solving the linear system now, and PETSC is lead to solving that. So PETSC needs what type of system? Yeah.
Right. That's true. Yeah.
Very good.
So once we have defined the constant forcing function, that's done. However, now is where we face some issues. Like when we apply the terminal load here, right? P here. The thing is, P happens to be applied at just one node.
Okay.
Then it will just be applied at the right end. However, it has some issue. So the issue is that Phoenix, even to this day, does not have a delta function in its armory. So I was just going through some blogs, and then I mean, I learned something from there that why we can use Gaussian function, very highly Gaussian function of very small variance. So you know that delta function is the limit of Gaussian function when variance tends to 0. So it's like maybe I'll just use a paint. I'm sure Seneca they know, so I'll still just for completing it. So since this is a Gaussian, and then so this is 0, and usually the tail ends at +3 sigma, and on the left hand tail ends at -3 sigma. And this will be some, I actually forgot, I don't know, if something related to 1 by some sigma, some multiples of sigma, I think √2 pi into sigma. So when sigma tends to 0, in the limiting case, this becomes a delta function.
Okay.
So delta function has, the way it's defined is delta of say x is equal to 0 when x is not equal to 0. But when x is equal to 0, then it has an infinite value. So a delta of x at x is equal to 0 is at x is equal to 0 has an infinite value. So that's why the way we define delta function is it only holds under integration. minus infinity to infinity of delta of x integrated over the entire real space or entire real line gives us a value of unity. So this is the, so that's why I mean delta is not a function. Mathematically, it's called as a distribution. So
Yeah, you should never call delta. I mean, you can never
yes,
call that function. Oh, this like yeah. You say
yeah,
you're stupid as soon as you say that. Yeah.
yeah. So in engineering, we have the habit of calling delta as a function, but delta is a distribution. So it's only valid under integration.
That's very right.
So what we are doing here is when we are trying to apply that point load at the end, at the tip of the bar, so we are using the substitution property of delta, which means that we are integrating from 0 to L, and then P is our terminal load into delta x minus L
Okay. Okay. So you convert this
into
into
dx.
you convert this into Gaussian.
Yes, so this is, we are modeling as a Gaussian.
Okay.
So once we know the theory, right, and in the what we have used is delta of x. One way of defining it is 1 by root over 2 pi sigma, or I'm using alpha. So alpha into e to the power minus of x minus L whole squared divided by 2 alpha squared. So this is the expression for delta. I mean, delta as a distribution. So I'll just call it
Gaussian.
delta D. Yeah, so the Gaussian. Yeah. So once, yeah, so which means that we are, this is how we are implementing our point force, point load. So now we are now coming to the theory. Now we can clearly say that, yeah. So I'm defining alpha, and then at first I'm defining something known as a delta temporary. So again, we have to derive a function from that same function space V. So we just define a function using that the same function space V, and then we are interpolating. See, we are interpolating that expression that we just mentioned.
Can you zoom in a bit?
Okay, sure, I'll.
Control plus should work, I think.
Yes,
Yeah,
yeah.
great, awesome. That's good. That's good. Yeah.
I don't know how to. Maybe I'll just do this here.
Looks good. Looks
Yeah.
good. Yeah.
So yeah. So alpha is equal to 0.015. So the what I had drawn in the figure is this happens to be already normalized.
Okay.
But here the thing is, we can also do one thing that, okay, we'll just divide by 1 by alpha into a square root of npi into e to the power minus x minus L whole square divided by alpha squared. So then we just integrate this over the entire domain, and then we can integrate this expression over the entire domain, and then divide that. I mean, divide our delta temporary by that integrated value so as to normalize the delta function. This I was just, I mean, I didn't have much time. So otherwise, the simple way is, why don't we directly have an interpolate the value, the actual expression, which is already normalized prior to doing all this. Yeah, but let's just have something complex so that we are also exposed to using this. What is this assemble of scalar? So just to know new functions, right? So that's why I have kept here that through this we are introduced to assemble dolphin.fem.assemble scalar as well as dolphin.fem.form. So here assembling scalar means that it will what it will do is, in the first place we want to integrate delta over the entire domain. So we are using the what do you call the mathematical programming language, right? That Dolphin, that the Phoenix package has within it. So we are doing delta temporary into ufl.dx. So this is equivalent to say integrate over 0 to L and then delta temporary, which is a function of x, and into dx. So this is what this expression does. And it will automatically calculate the integral, and then it assembles as a scalar. So as per the as per the documentation, it says that it is used to assemble functional. The return value is local and not accumulated across processes.
Okay.
So yeah, I think this right now it's beyond the scope of our lecture, so I won't be discussing what is accumulated across processes or return value is local. So right now we'll just keep it at that. Yeah, that it just assembles, it just gives us a value, and then so this is our delta function.
So
Once
you're
we have
essentially
that,
trying to write Gaussian, no? Writing Gaussian using all this
yes,
stuff, right?
yes.
Yeah.
So it would have been
It's
just a simple line code, but we want to learn these new functions because it often comes in handy later.
exactly. So it's like that black box is Gaussian function. They're trying to put like
Yes.
function there.
So by here, this is the Gaussian function, delta. And then we also define this P. P is our terminal load, but we still have to define it over the domain. So we'll define throughout the domain. You see P is equal to dolphin.fem.constant. And then we define over the domain using pet.sc, scalar type of value 1. And this is our external node. And you'll be wondering, but why are you defining over the entire domain? Yeah, so the thing is, this is the only way we have right now. But when we are enforcing it, we'll still be enforcing only at that tip, and we'll see it right now. And then
But
now we define our variational problem.
Okay, I got it. Yeah.
Yes. So now we define our variational problem. We define dx. Dx is our the integration element, and then it's defined over the domain. And now we define the second thing is our
TDE.
yeah. So A is equal to E of A into UFL dot inner UFL dot grad U, comma UFL dot grad V. You see, right? So we are defining gradient of U and gradient of V. And in 1D, gradient of U is equivalent to U prime of X. Likewise, grad of V is equivalent as V prime of X. So this we have defined. So variational problem is essentially A of, so this is what is the variational statement in FEM.
Yeah.
Yeah. And then for L,
for linear,
for
no, for
linear.
non-linear is different and everything. Yeah.
Only for linear problems. So what in the thing, I mean, the thing with nonlinear problem is then A will no longer be bilinear, but we can even write for, this is applicable for both. It's applicable for linear as well as nonlinear, both. It's applicable. But the thing is, then the properties of A, which was bilinearity, does not hold. So it doesn't make any sense to cast in this form. But we still can do. We can still solve it using the same form. Then we won't be using linear solver. We have to do it. We have to use some Newton-Raphson iterations to solve such problems. Now the interesting part here comes for the right-hand side, because right-hand side is the tougher one here, right? So L is equal to F into V into dx. So this gives us, here F is our constant forcing function, which has a value of 6 throughout the domain. And then we have U of UFL dot inner. So we first define an inner product between P into delta. Now recall that P into delta will be such that the effective P will only be at the tip. At other points, it will just be 0. In fact, it will be so small that it's just equal to 0. And if you really want to make it as closer to 0, we just have to decrease the alpha value, make the delta function much more sharper.
So delta is like what we discussed, and P is the function load value you're giving, like 1 into delta, 2 into delta. So you'll get that value at that point, no?
Yes, at that point only. And although the thing is, we have defined P throughout the domain, but when it acts on the when it during in the formulation, after all, it will only act at the tip. That's it.
So this is the way to give it, no, for
Yes.
for the variation problem L. So you
Yeah. Yes.
right hand side you give it like that. Okay.
Right.
Cool.
Okay, so once we have this, now our goal is
You
to define the.
commented this F varying. Why did you comment that F varying
Yeah,
stuff?
I can still have. I can still have. I just wanted to
Okay.
check out whether I'm just while debugging, right, just to see if F varying has influence or not. So the
No
influence
problem.
was
Yeah.
there. I said, okay, now it's working.
No problem. Yeah.
Okay, and it was giving some sinusoidal behavior in the solution, which is as expected because we are giving a sinusoidal function also, right?
Yeah.
Okay, so once that is done, now we'll define the boundary conditions. And for that, we need to determine all those nodes on the left-hand side, on the right-hand side.
Yeah. We have discussed this last week. Yeah.
Yeah.
I can't. Yeah. You there?
Yeah, so now let's determine the left degrees of freedom. And then again, since degrees of freedom is a part of FEM framework, so we'll be using Dolphin package, dolphin.fem.locate DOFs geometrical. This is the function name. So as per the documentation, what it does is it locates degrees of freedom geometrically using a marker function. So marker function, in this case, it's left. Left is a marker function, which means that it will take all the nodal values and it will return a binary array, such that it will just give us which node actually is at the leftmost. So you see, right? We are using np.isClose. So which node is closest to 0?
Okay.
So it will just give us the left end. And rightwise for right dots, we can use which is the closest to right end, which is the closest to the length. So
If we move,
all I'm just computing both just for our just to what you call, for us to understand how to determine this, but we won't be using right dots. So once we have the right dots, now what we need to do is collect everything into a single array, all the boundary conditions. You see, right? So BC is equal to, so we use dolphin.fem.dirichlet.bc, and we prescribe what value we want to give. So the value is petc dot scalar type 0, and the which for which degrees of freedom. The degrees of freedom are left degrees of freedom, and which domain. So domain is V, or which domain, or in the sense that which particular function space. So this is V is equal to V. Okay. So once this is done, now we are ready to solve our problem. So for that, we need to import dolphin.fem.petc. So we will be using petc library, and now we what do you call, create the function, or so the function, the create the problem. So the problem is defined as dolphin.fem.petc.linear problem, since this happens to be a linear problem. Okay, so
okay.
initialize the solver for a linear variational problem, and then prescribe A, L, and where we would like to what you call, keep the solution. So it is U is equal to usolve. That is where we use it. Had we not prescribed usolve, then it would have returned a U here. It would have written U. So why not better to prescribe before only that, okay, we want to store our solution in U underscore solve. And we give the
Okay.
BCs as an argument, and the options for PET-C. So the options are KSP type is preconditioner only, and the preconditioner type is LU factorized.
So I'm just wondering. I think in one of the tutorials we should just look into PET-SC, like PET-SC for Python, like what are the linear equations and what are all the ways to solve, and maybe I don't know if it's
I
actually.
think that would be the best way. Yeah. In fact, even to discuss all these building blocks of Dolphin package,
Yeah.
and that would be a wonderful exercise, because we would like to know all these PET-C options as well. So these PET-C options will depend on which problem we are solving and this on the structure of the matrix system as well. And now we finally problem.solve actually solves the problem. And then what we do is we define a VTK object. It is equal to dolphin dot since we want to do some file writing. So we use this IO class of dolphin package and dot VTK file. So we want to have in VTK format. And then we define again, we have to prescribe this mpacom world. And then what is the file name? So the file name is output.pvd and W indicates that we are going to write in this file. So W is the instruction. And then vtk.write functions u underscore sol actually writes, you see, right? So it writes everything to this file. And now we come to post-processing using matplotlib. We can also plot the results right here. So I'm telling that cells type X. Now we can define what you call what all cells and what are the coordinates in this function space V, and all the plot parameters. And then we are finally plotting it. The difference it be is because the exact solution was computed only for so it was computed only for the constant coordinate function, right?
No,
Yes.
yeah.
So which means that what we can do is I hope I have
Yeah, it's great.
so I'll just we can just finish this by giving the actual solutions for the general case, right? So let's use Mathematica to do that job. And so today what we'll do is we'll start some hyperelastic, although I have not prepared any code for that, but we'll just go through some code by one of the principal developers of Phoenix package. So before this, let's just write what are the parameters required. The parameters required is we'll have bsolve. Oh, before that, we just have to say E is equal to 10, and not just 10 for 9, isn't it? And then A is equal to 0.01, and then so we'll have F varying. So this we use 10 into sine of 2 pi to x, and then F is equal to F is equal to, we used a value of 6, isn't it? Yeah. And then E is equal to 1. So now we'll use solve. What we want to solve. We'll like to use this dsolve function and then prescribe the differential equation, which is E into A into U double prime of x plus F plus F varying is equal to 0. The boundary conditions are U at 0. Then we forgot to prescribe L, so L is equal to 1. So U of 0 is equal to 0. And then E into A into U prime of L equals to E, then U comma X from 0 comma L. So let's see what it solves. Damn. Giving too many output, huh? Okay. We always need to go through the documentations again. What's the issue here? Okay, so it's essentially giving us the solution, right? Yeah, it's giving us the solution. This is the solution.
Okay.
So it's like 119.966. So this solution plus this as well. Till here. Copy and then we'll just paste it in our notebook. Essentially, we just want to compare with our analytical solution. Let's see how true it is. So u comma underscore exact. So it's like into x of all nodes, and then likewise comma 0 and np dot sign, and this is nothing but 2 into np dot phi. And this is yes. Let's hope this gives us the actual solution. N is to okay.
I think it is okay, Krishna. I mean, because we are only to FEM here now. Even it's wrong. I mean, right? Let's not stuck here and probably
Yeah,
let's
that's
let's
what
let's
it looks so. Yeah.
yeah. You can give it just homework probably. Up to you. Yeah.
Yeah, I understand why this is giving such an issue because they only take y. E is reserved for their
No, I think it takes. They're not like easy to just अभी solve किया तो not Fibonacci series, no.
ha.
Anyways, yeah.
So this is the one. Actual solution is this. Minus 2 minus 7 likewise here, and this is 2 point into this one. Yes, I hope this works this time. You see, right? Yeah, it's
Oh,
matching.
yeah. Excellent.
Yeah, so with this we are done with our problem. Maybe what we'll do is let's just go through some of the lecture notes right now.
Okay.
Because I have shared all the references, all the resources here in this folder, in this file called Phoenix resources.
Okay.
And then we'll just have a look at, maybe we can start with Blair.
Okay.
So Blair has a very
Yeah.
good resources on quantum
Can
mechanics.
I see the other resources as well? Can you please go back to that?
Yeah. So this is
Shell.
the first resource is the most important one. It is by J.S. Dokken, who is one of the principal developers of FEM Phoenix package.
Okay.
And the second one is by Blair, which he is more solid mechanics oriented, and we can clearly see, right? Everything, all the topics that he covers are from solid
Yeah.
mechanics.
If you actually go down to this welcome thing, there are more resources. Not here
Yes,
in the website.
this one.
There is something called this David Kamansky mixed. If you go down now, bottom. Go on, no, in
This
that one. Go to bottom.
okay. In this you may know, or
Here, if you go,
I see.
there is. पूरा नीचे he हाँ थोड़ा ऊपर जाओ.
This
I
one
think
you
he
mean?
gave some resources here as well.
I see. I see.
I'll
Okay.
share it. I'll share it. David Kamenetsky. Yeah. Finite element mixed FSM. Anyways, now I can't find it. So.
I see.
Yeah, there we go. So here I'm just sharing on the chat.
Okay. Okay.
Putting in the chat. You can check that drive thing. Okay.
I see. Okay.
So this is for mixed formulation, which we may look into it in future, hopefully, because the pace we are going, I think we can touch upon this.
Yeah. We'll. Before that, I'll
So
just give
this
a
was
yes.
so this was given in one of the resources in those things which you shared in the websites which you shared.
I
So
see. I see. Okay. I recall having downloaded these notes once. Yeah.
is it? Okay, let's go back. So you were discussing about
Right.
the
Yeah. So essentially, we'll just go through some of the notes here, and later I'll give a short Phoenix. I mean, Python tutorial to our Dr. Pinika.
Oh, Chinika
Yeah,
doesn't know how to use Python, huh?
yes, I mean, she is an expert in MATLAB, but yeah, Python, yeah, it's like,
Yeah, it's okay. It's easy.
Don't say Krishna expert.
Maybe excellent, probably.
Mhm.
it's expert in the sense that, yeah, you can code whatever is given.
Yeah,
Yeah.
Yeah.
if it is possible in MATLAB, after which I
Yeah,
know
that's right.
again.
That's right. So
Krishna
here, yeah,
is expert in both MATLAB and Python, which is I am not.
still
Okay,
trying
let's
to
do
learn.
it.
Yeah. So, yeah,
So do
we'll
you
start with,
want to do this Python thing in this tutorial, or you want to give it to her separately?
yeah, I'll give it separately. Yeah. So because today we are not
Think
going
about
to code this, we'll code it in the next session, all this hyperelasticity, yeah, and all these event, Reisner-Mindlin plates. We'll do all this, including all the problems here, because all of these problems are very worthwhile. Say even say linear shell model and everything.
Exactly, yeah.
So actually, so in this happens to be what he calls as tours. So these numerical tools are intended to complement the existing Phoenix tutorials in the official documentation by focusing on specific applications. Maybe I'll just zoom in. Yeah. Yeah. So based on specific applications within the field of computational solid and structural mechanics. So the purpose of these tools is to offer users with a background in mechanics a starting point for utilizing Phoenix. While many of the covered topics are standard and relatively easy to implement, others such as structural elements, beams, plate cells, or nonlinear constitutive models present more complexity. Other topics will also be more advanced and exploratory and will reflect currently investigated research topics illustrating the versatility of Phoenix for handling advanced models. The difficulty of each store will be indicated by the star symbols. First star means easy and triple star means difficult. So now let's just start from the first tutorial, which is linear elasticity. Although we have done, there is just like a overview. So it's like in the context of solid mechanics, the variational form within a small strain setting this is how we'll define our weak form. So yeah, so integral of sigma over u, doubly contracted with symmetric component of v, and is equal to f dot v plus this is the boundary contribution to the to the forcing function. So and so
Mhm.
this is how we'll directly code even in the Phoenix platform.
Mm.
So here you use the unknown displacement, and it's the trial function as we had mentioned even in our tutorial code tutorial, and it lives in the space of admissible displacements V, such that U is equal to U naught on the Dirichlet boundary.
Oh.
Krishna,
Yeah. Yes.
small v is
Mhm.
test function, right?
Right. Yes. Yeah.
Why are you taking the gradient of test function? Did you discuss
Yeah.
this or not?
Recall we had done a similar approach, right? In our that we had
Yeah,
transferred
yeah.
the second
dv by
derivative
dx.
on
Okay,
U.
fine, fine,
Yes.
fine. dv by dx, which is yeah, chain
Right.
rule.
Yes.
Yeah.
Yeah. Uh-huh. And then we use F and T, respectively, body and surface traction forces. So F is our body forces, and T is our surface traction force. And sigma of U is the Cauchy stress field, which is nothing but C doubly contracted with grad symmetric. So this S superscript here indicates the symmetric part of the grad of V.
Mm.
So the way we define is, I'm sure we know, but still, just for the sake, uh, come on, why is it coming like this? Okay, damn, maybe I'll open new one. Yeah, so in this case, what we are essentially doing is grad of S as an operator is equal to half of grad operator as an operator plus grad transpose, yeah,
Mhm.
as an operator, yeah.
Mm.
So this grad transpose happens to be nonlinear. I have seen people calling it because it complicates a bit. So grad transpose is something which essentially involves coupling between terms. Yeah,
Okay.
so we'll discuss about this sometime later, but yeah. So
Mhm.
yeah, that was the and then V indicates the test functions, and then it will carry a zero value on on the part of the boundary where we have prescribed Dirichlet boundary conditions. And this happens to a weak form of the equilibrium equation, and we need some constitutive relation which will relate sigma to U. And so for this, we use that generalized Hooke's law, which is capital C is our
Mm.
elasticity tensor, and it's doubly contracted with the grad of symmetric grad of U. And C here happens
Mm.
to be a fourth order tensor. So even after doubly contraction, it will result in a second order tensor.
Mm.
Yeah, and as usual, we would be using what we call as the what is that, Voigt notation, so as to transform even sigma from a 3x3 system to a 6x1 system because of its symmetricity.
Mhm.
Yeah, so now we have this. So this is our equilibrium equation. I mean, the weak form, which we will essentially implement in Phoenix. And now you see, right, that this this integral here happens to be bilinear, which means that it's linear in U as well as linear in V.
Mm.
So that is why we call this it has the bilinear form. And on the right hand
Mm.
side, it's linear with V throughout. Both the terms are linear with respect to V. This
Okay.
can be written in this AU of V is equal to L of V for every V which belongs to V naught. And naught here indicates that V will have a zero throughout. Throughout the boundary, V will have a value of zero. So that is why we use this subscript naught.
Mhm. For test function only. Huh?
Yeah, for test functions only, right? Yes.
Okay.
But I think there is some confusions here because I see that they have also some traction boundary condition also. So on traction, we will not have a value zero. So I'm just wondering why they have used V naught. Okay,
Mm.
so it's like they should not use V naught because V naught will indicate that it has a value of zero throughout the boundaries. But anyway, yeah, so now we come to the implementation part. So just as a
Mm.
review, right, we had this multiple of packages. So UFL, it does symbolic expressions. and it handles using this UFL package, which allows to combine abstract operators in a notation close to the mathematical one. And UFL also provides the test function and trial function objects appearing as arguments of linear or bilinear functions. And Dolphin X is the Python interface to the computational environment of Phoenix. It provides all the necessary tools to load meshes, and it even has the power to do meshing right at the spot for simple geometries. And then we also use it to handle data structures and functions related to finite elements such as global FE function spaces, the associated functions, and the assembling processes, as well as to define boundary conditions and also to set the the solvers. And some other packages are MPI4P, which is nothing but the Python implementation of MPI package. MPI package was originally written for three different languages: C, C++, and Fortran. So still MPI is actually uses C language much more efficiently than C++, but that's another story. And PETC is it's to to perform linear algebra in a parallelized framework, and FFCX is what we call as the just-in-time compilation of forms. So it's like when we describe any expression, right? Like the way we have described the expression here, if you go back to the code. So the way we have described this expression here, the inner product or all that, the thing is the software does not know how to deal with it beforehand. So it will do just-in-time compilation, which means it will actually convey this to the C++ backend and then compile that particular part to actually solve the problem. Yeah, that's why it's known as just-in-time compilation of forms. And we had used form explicitly at one place, which is here. Okay, we had explicitly used dot form. So it does this integration real time. I mean, by real time translation of code. So here for the problem, what we are doing is we take a 2D rectangular beam of dimensions 10 cross 1, which will mesh with quadrangles. And quadrangles is nothing but, it's just like, I think we very well know, it's just like this. Right? And these are known as quadrangles. So since this is a simple rectangular framework, right? So we can just use the simplest meshing. Okay, and we'll first start by loading the relevant packages and functions, and the dolphin.mesh will provide a customary function for meshing a rectangular domain. And for more complex cases, we can import meshes generated by external tools such as Gmesh, for instance. So actually, Dinesh, Chininkandi and me, we had worked on doing this. We actually imported mesh by creating it in Gmesh and loaded it into. Yeah, I have. It was long back, 1 year back. Yeah. So we still have those files with us. Yeah. So we actually use the Python interface to Gmesh package, and then define the geometry, meshed it, and then import it into Phoenix.
Okay.
Yeah.
That will be interesting to do actually. Yeah.
Right. That's true. That's true. So since the code is already written, so we'll just have to run it and also, I mean, look at how the mesh is generated. Okay, so coming back here, we are imported all the necessary files and and all the classes and all. So one way of importing is like this, but I always want to get the actual path. So what he will say is, you see, right? He will use from UFL import grad import inner library inner import measure. But the thing is, sometimes it becomes confusing. So it's one an advice to sometimes to code is that we should always give the full path. So it helps us to understand which function is located in which class of which library. So that's why I use the full definition. But I don't know. I mean, it just makes the code very verbose, but at least we know which function belongs to what library. So once we get a hang of that, then this is the better way to do all this import business. We'll prescribe from which package, which all functions do we want to import. Okay, so coming back to the problem here, we define length and height of 10 and 1, and the number of elements along x along the length direction is 50 and along height it's 5. And then we use this create rectangular function with from dolphin.mesh class. We prescribe the communication network, prescribe the diagonal ends of the rectangle. So 0, 0 is the it's what you call the vertex located at the origin, and length height, this is the vertex located at the extreme at the at the other end of the diagonal. And then we have mentioned how many number of elements we want along which direction, and then which cell type. So he has prescribed that we want a cell type quadrilateral. Once this is done, now we can just get the dimension of the topology. So since the topology here in this case happens to be a 2D framework, so it returns the mesh topology as dimension of 2. Now we'll come to define the finite element function space for our U solution. And since now we will be dealing with a vector function, right? Since we are dealing with our 2D problem, now we'll have a vector function. So here we use a vector function type of P is polynomial, which implies standard Lagrange elements of degree 2 here. So he'll be using second degree polynomials to do the for the function space, or to define the basis functions. So we come to here. So degree is equal to 2. Degree is equal to 2, and shape is equal to dimension. Dim comma, what you call this means that we want a vector field of size dim, right? So we have to prescribe which. So before we didn't have to do this shape because we were using at every point the value of the unknown just happened to be a scalar. But in this case, we'll have a vector. So we have to give an additional argument. So till here it was the same for us, but now we have to define what's the shape of that unknown at every point. So once we define the function space, we are doing the same thing. Again, usol is equal to fem.function. Over the domain, we are defining a function whose marker, who is marked as a displacement. And then we'll use the various UFL expressions, which will help us to construct a variational formulation. And so since the Young's modulus has to be prescribed throughout the domain, so FEM.constant, it takes two arguments, the domain as well as its value, and nu is our Poisson's ratio. It also takes FEM.constant, domain, and the value of 0.3, which means that it's a compressible medium that we are looking at. And then on what you call, we are defining the lemma parameters as lambda, and mu in this form, that E into nu divided by 1 by nu into 1 minus 2 nu. And for mu, it is nothing but our shear modulus, which is E by 2 into 1 plus nu. Likewise, we can define what do we mean by epsilon. So epsilon will take some argument, and then it will return the symmetric part of the gradient of V. And sigma, which is the stress component, what it will do is it will multiply lambda into trace of epsilon V into identity of dimension 2 plus 2 into mu into epsilon of V. And this we can just check whether they are really UFL expressions. So if we print it, we get all these symbols, which just says that, yeah, we are using the FEM, we are using the UFL package to get all these expressions for all these operations. Now we come to defining the linear and bilinear forms. So we have U as a trial function, V as a test function. We define rho, which is density of the medium. G is the acceleration due to gravity. And then we define this F. F happens to be our source function. So F is equal to FEM.constant defined throughout the domain. And the forcing function in this case happens to a vector, and it will be acting in vertically downward direction. So that's why it is minus rho into G. And then we define the integration element, which is dx. Now we also construct what we call as our bilinear form. So A is equal to inner product of sigma of u, comma, epsilon of v into dx, and then L is the forcing term is equal to inner of f comma v into dx. Now, once we have defined the bilinear form, now we'll also prescribe the boundary conditions. For simplicity, we first fix both the left and right boundaries. To do so, we must locate the corresponding degrees of freedom from a marker function that returns true for points x on the boundary and false otherwise. And so for the left, what we do is we are just comparing the x coordinate to be zeros. So in this case, left will be a face, right? So we are essentially determining this here. So it's for all the points here, x coordinate will be 0. And on the right hand side, for all the nodes on this, we'll have x will be equal to 10. Yeah. So that's what we are doing. So once we have defined these functions, now we use that locate GOF's geometrical. You see that? So once we are locating the geometrical component, I mean, all those geometrical degrees of freedom with our degrees of freedom which actually exist for that geometry, then we have to prescribe or we have to give as an argument the complete function space and the marker function. So what it will do is it will pass all the spatial coordinates in that domain and match with left function. It will let it pass through left function, and it will just for every node it will give us true or false. So if it happens to be on left, it will get true, and then this function will only collect the nodal degrees of freedom for those nodes. And likewise for right nodes, we do the same. And now we are prescribing boundary conditions for right and left DOFs. So recall in our code also we had used FEM or Dirichlet boundary conditions. And since here we are actually defining a vector, we have a vector unknown at every point. We'll have to prescribe np dot zeros, both the components to be zeros on the left degrees of freedom and on the right, and also giving the complete function space. Likewise, for right degrees of freedom, we are just repeating the same thing. So with this, we have created an array containing all the boundary conditions, or just a list of all the boundary conditions. Now we'll construct our linear problem. So the linear problem is created based on the various problem, the boundary conditions and the function u in which we want to store the solution. We can also pass parameters to set up the solver type. Results are then stored in a PVD format to be visualized using ParaView. So similar to what we did, we have to give the following arguments to the linear problem function in PETC class of FEM subclass. So we have bilinear form defining the solution, where to store the solution, the boundary conditions, the options that we want the solver to have. And then we solve the problem and to store the solution. And this is a little bit complicated part, so we'll just leave it. We'll discuss it in another class about we can also constrain certain components. So we can constrain that, okay, the say the x component is 0, but y component is unknown. So we can do that also. Yes. So this will
It is like
discuss
simply
next.
support beam and
Exactly. Yes. Yeah. So which
right?
means that say we so something like on one side we are prescribing a roller.
Yep.
Yeah. So it's like we have this body here, and although it's not allowed to move in x direction, it is allowed to move in y direction. So we have a roller. So it can move vertically upwards and downwards, but it cannot move this side. This side is not allowed.
Exactly.
Not allowed. So these are like more complicated boundary conditions, and we'll actually come. Or maybe, I mean, the thing is this, I will have to go through it once more. So,
Okay.
yeah. So till the next class, we can actually discuss about thermal strains. We can even, what you call, write a code for this. But for now, we'll start with hyper elasticity, because I think we need to enter into hyper elasticity today. But we'll be discussing the code again in the next class, solving those example problems that he has given. Okay, so here we will just be build upon the previous one on linear elasticity to formulate a nonlinear problem arising from finite strain elasticity. And the symbolic differentiation capabilities of UFL will be very useful in such examples. Okay, so now let's start with our problem. So we'll use a total Lagrangian formulation. So in total Lagrangian formulation, what we do is we always study the displacement of the materials vertical from the material frame perspective. So it's like we fix the frame, we fixed our domain, and then calculate displacement of any point without actually displacing without actually, I don't know how to say it. It looks like I'm just confusing you all. So the way we do that is delete this and it goes. So I'll just open print. So in total Lagrange formulation, what we do is once we have a domain, so this is the undeformed domain, and then this is the deformed domain. So this is the deformed domain. So this is the deformed domain, and this was the undeformed domain. So what we do is, so given any point x, right? So say this has the what you call Poisson vector x. So, and we would like to get the deformed shape. So our goal is to determine what is the displacement function which actually gives us this deformation. So this x will be located, in this case it will be here, right? After deformation it will be somewhere here. So if this is point P, this is still point P, but P prime, which means it's in the deformed configuration. So our goal is to determine U. So the Poisson vector of this from the in the Cartesian system here will be the Poisson vector will be here x prime. So the relation between x prime and x is x prime is equal to x plus u. So our goal is to, this is the unknown. So in the total Lagrange formulation, what we do is we always work in the reference configuration, and our goal is just to compute v. So all the integrals, everything will take place in the undeformed configurations. You will see every integral will always take place in the undeformed configuration. So you'll always see that everywhere there will be just sigma naught. Ideally, so this is sigma naught and this is sigma, right? The deformed config is sigma, and this is sigma naught is the undeformed config. So all the integrals will be carried out in the reference configuration system, and we'll use something known as pullback. So any deformation will always, any function will always pull back to the reference configuration. So that formulation is known as total Lagrange formulation. So total Lagrange formulation is very it's very used, very much widely used. However, it does have limitations also. The advantages are that you are always working in the reference coordinate system, reference configuration. So that is a very big advantage. But there is a demerit when, say, if a body undergoes such large deformations that that's the mesh quality can become very, very poor. So in that case, what we would like to do is we would like to progress systematically from say, if this body undergoes very large deformation, say something of this sort. So this will like completely it's like u is very much large compared to x, isn't it, for problems like this? So
Yeah.
in that case, total Lagrange formation is not recommended. So what we would do is we would like to always keep on changing the reference configuration. So we would like to approach this through a series of deformations. So say we'll apply something that it deforms like this. Okay. and apply some more load so that it deforms like this. So we will incrementally increment the loads gradually. And at the same time, we would also be remeshing it. Remesh.
No, I think I have a like I have
Remesh.
kind of not objection, but I have a like I want to say something here.
Yeah.
So I think we still want to use total Lagrangian formulation, but
Mm-hmm.
you can't. But you should keep on updating your reference configuration. Else it will be that's not right. Else you can go for Eulerian, like not Eulerian to नहीं
Yes,
कर
yes,
सकते
yes.
इसमें, right?
Right. We
So
cannot
if
do
you
so.
still want to use, yeah, if you still want to use total Lagrangian formulation, then you
So I
update
think
your
remesh is a,
reference configuration time to time, right?
yeah, it's like I just overstate. We don't remesh it. What we do is we just update the reference configuration.
Yeah.
It's like when we move from here to here, we'll update everything and we'll carry out all the integrals in omega. And you know omega will
Okay.
keep on changing. This omega is first omega, then omega 2. Likewise, till we obtain the final equilibrium shape or equilibrium configuration. Still here, say omega n. So we'll keep on. So for omega, when we are determining omega n, our reference configuration will be omega n minus 1. So it's like we are incrementally approaching the final deformation using a series of initial configurations. So that is what we use, what we call as the updated Lagrangian formulation. Yeah, it's used only if there are such severe deformations, right? That if we directly use total Lagrange formulation, it won't allow the solver to converge. Then we just proceed it like systematically, one step at a time. There was just a small brief digression from our topic here. So here, in this case, our weak formulation will be P doubly contracted with grad V into d sigma, d omega. And this is equal to F dot V d omega plus T dot V ds. Now, these terms on the right are the same. It's only terms on the left that we see some different things come into the picture. First thing is, what is this P? Now, P is called as the first Euler-Kirchhoff tensor, and P happens to be it's known as a 2-point tensor. So maybe I'll just stretch this. Come on, open a new pen maybe. So what P does is, P happens to lie in both configurations. So P tensor, the way it is written is, it will so I mean, making it understand from a practical point of this one, right? So say when we are stretching a bar,
Okay.
I think this is very much widely known in our mechanics, this one, right? Solid mechanics or strength of materials, I believe. So when we are stretching it, before it was a straight bar, uniform bar, but as we stretched it, so you see there are like some lateral deformations come into the picture. So which means that say if the area of cross section was A here and it was uniform throughout, but now what we see is at different location our area keeps on changing. Area has become a function of x. So although the force remains the same, F, and here also F. The force is the same because we are applying dead load,
Yeah.
but it's the area is changing. So which means the measure of stress will change. Here stress will be something else. Stress is something else. So we'll just call it, let's just call it something, some say sigma 1. And this stress will be sigma 2. And we know very well that sigma 2 will be higher than sigma 1, right?
Correct. Because divided by area, area is lesser.
Yes.
Yeah.
So what we do essentially is, we still want to have, we still, what we call, we will, when we try to find this, so when we find, say, when we are drawing stress strain curve, right? Stress strain curve, in what we see in the literature, right? The classical literature, they will define some stress versus strain. So in the stress, what they do is they don't actually measure the actual stress. They actually keep the same area still. They don't change they still consider it as if the same area is existing, and they will just do say F by A. And they will keep on varying F. F will be varying. And then A will remain the same as A naught, which is this A naught. So you see that although the force is in current configuration, area happens to be in the reference configuration.
Yeah.
So
That's
which
for
means
engineering
that
string. That's not engineering. What do you call that actually?
yeah, this is what we call as the engineering stress.
Stress, right? Engineering stress, yeah.
Yeah. And actually, engineering stress is a very colloquial term for first Piola-Kirchhoff tensor.
Okay.
First
Okay,
Piola-Kirchhoff, first PK stress.
Mhm.
So now we understood the idea behind P. So what P does is it actually takes both the configurations into account. It uses area from the current configuration, from the reference configuration, and the force from the current configurations. So now by now you realize that P will have indices say I into say capital I. So capital I denotes that it's the index defined in the reference configuration, and small I denotes that we are also dealing with traction. I mean with the current configuration. So that is the thing with P. So P, you'll always see that whenever we write total Lagrangian formulation for say nonlinear problems, we always use the first Piola-Kirchhoff tensor stress, because it's first Piola-Kirchhoff stress which is actually measurable.
Okay.
Rest are just constructions, like construction in the sense that
Of course.
we do not know how to measure both at the same time, right? We only measure force, how much force we're applying, and
Yeah.
just how much stress there will be. So it's like
Yeah.
something which can be measured. And I'm sure we can still measure Cauchy stress also, but
No.
again, we need to do a lot of image processing and all to understand that.
I think this is actually important to discuss. I mean, we are not looking at it in a practical point of view. Say you are designing something, okay, and of course, since you are taking the real, I mean, engineering stress, and you assume engineering stress throughout the material life, then the actual stress is different, no? You understand?
Right.
So
Yeah,
we
yeah.
might get body into failure sooner than what we thought because we are not considering real stress. Correct? Do you
Yeah,
understand
yeah.
what I'm trying to do? Yeah.
Right. That's true. That's true.
Yeah. But anyway, so yeah.
Yeah.
Okay.
So once we have this, now what we do is in the case of hyperelastic material, the constitutive relation derives from an energy function which is psi of F. And it will depend, and psi is the free energy potential, and it will depend on the deformation gradient. F is equal to I plus grad of U. And U here is what I was defining here, right? It's known as the displacement function.
Yeah.
So U gives us how much a material point has displaced from its original configuration. So that is why it's known as displacement function. And if you call X, right, X is just a mapping. So when you call, say, in quantum mechanics, we'll call this X prime, but they will usually call it as what you call X in lowercase letters. So this is known as deformation mapping. So X is equal to some mapping phi of capital X. So this is just what we call it, the value of the deformation mapping of a material point. So once this is done, so our problem is to the above nonlinear variational problem corresponds in fact to the first order optimality condition of the following minimum principle. I think we had discussed some time back that every what you call we can always have weak form for any equation, but not every weak form can actually be obtained from a variational problem.
Yeah.
So which means that so say when this author writes that we are actually minimizing this energy function. So which means that it's already understood that this system happens to be conservative in nature, and that's the reason it has a minimizer, non-zero minimizer. Okay, so now we come to problem form. Yeah, so now we come to what the problem essentially here is. So we consider a cylinder of square cross section, which is essentially a way of telling that it's a cuboid. A cylinder of the square cross section is essentially a cuboid, which is fixed at its bottom edge and to which we impose a rigid rotation of the top face of angle theta about the vertical axis. So it's a complicated problem that we have a cuboid and then the upper face we are giving a twist.
Oh, this is a very famous problem, dude.
Right, yeah.
Very famous problem.
So yeah, these are problems which are used to analyze.
Go to the figures. Is this 3D or 2D?
It is a 2D. It's what he has written is 2D problem, but let's see where it comes.
Can you go to the figures like it?
But I think it will be a 3D problem. I think it will be a 3D problem. It must be a 3D problem.
Go to the figures. Hopefully, you can. No figures.
Yeah, not figures. Yeah.
It's a 3D problem, dude, and it's very famous. Hyperelasticity.
Yeah.
In any total Lagrangian formulation, no. They have to validate a benchmark, no. They take this problem, and even you have something called. So this problem has some issues in FEM as well. So I forgot the issues. Is actually basically has like FEM can't solve this, so they will add something more to the existing FEM, and I'll share it. So I'll share it. Right. Sure, the next lecture probably. But yeah, famous problem. Certainly. Yeah, thanks.
Yes, certainly. Yes, yeah. Okay, so once we come here, yeah, and then we'll start with a simple compressible new Hawkian model with psi of f is equal to mu by 2. I1 is the first invariant of the trace of C, minus 3 minus 2 log natural of J, plus and J happens determinant of f plus lambda by 2, J minus 1 whole square. So now just to check whether this energy function is feasible or not, right? So in quantum mechanics, we define that the energy function should always be greater or equal to 0. And it will be 0 when there is no deformation, right? Hello, I hope I'm audible. Hello, am I still audible?
Sorry, I was just away.
Okay, I hope I'm still audible, right? So I just wanted to say that in quantum mechanics, the way we define what you call energy function, right? That it should be always greater or equal to 0, and it will be 0 only if there is no deformation.
Yes, of course, the energy, no. Now, I mean, how can it go negative?
Yes. So we would like to see whether this is really true in this energy function, whether it is right energy function, right?
No, is it energy or potential?
This is the strain energy function. Strain energy. We call it energy function.
Yeah.
Correct. So let's just check, right? So say if there is no deformation, F will be equal to identity matrix or identity tensor.
Yeah.
Because in that case, U will be equal to 0. So it is just identity.
Yeah. It simply maps. No, it is just rigid motion. So U has to be same, right? That's the point.
Yeah. Yes. Yeah, that's one thing. And the other thing is if there is no deformation, say it's just kept as it is. Then in that case, F will be equal to I. And then, so F will equal to I. So it will F transpose I is nothing but I again. Isn't it?
Yeah.
I transpose is I. So I, and the trace of I is the sum of the diagonal terms, right? Which is 1 plus 1 plus 1. 3. So we put P here. So 3 minus 3 is 0. And determinant of F, which is equal to determinant of identity tensor is 1, right?
Log 1 is
1. So which means that this is 0, and likewise this is also 0, which means that it is a valid energy function.
Okay.
Here obviously it is tested, but in general, if we say, right, if anyone gives us the energy function, we must first see whether it really is 0 at 0 deformation. Yeah.
I see your point. So you're teaching us to see, this condition solves it or not. Yeah.
Yeah. So now we come to implementation. So we are importing all the necessary libraries. Now we see.
Can we stop here probably because it's been
I think that would really be nice. So what we can do is we'll just give an overview. We won't read it, but you see some differences coming here, right?
Yeah. So you
see
have matrix. Okay.
NLS. We are importing one new function, which is NLS.
Okay.
So NLS stands for non-linear solver.
Okay.
So even here we see dolphin.nls.petsy. We are using petsy library, but this has been implemented in NLS class.
Okay.
So that is the important thing here. So which means that essentially this is a very nice tutorial. In fact, we should complete all those tutorials and understand it very well, all this tutorial. And you see, it's not a very big tutorial. It happens to be just a reasonable. It can be done in next time during the next session we'll be doing. We can do even in between the weeks. So it's like
So I think one thing I want to do is I want to look at this pet SC thing independently, and maybe I can present a little thing if that is fine. Hopefully.
Yeah, but
So?
that is also one thing. Yeah, and the other thing is I think it's better if we can try to finish as a tutorial so that we are in a good platform to start studying implementing shell theories.
Yes.
Simple ones.
I agree. Okay, so our first target is to
maybe
get to
I'll
shell
just
theory.
stop sharing. I will just stop recording so that we can discuss other ideas.
Please. I'll put my video on.